In this video, I'm solving a first-order differential equation involving the unit step function using the Laplace transform. So in this example, I'm solving y prime plus 3y is equal to u of t minus 2 with the initial condition y of 0 is equal to 1. So the first step is to apply the Laplace transform to both sides of the equation. So using the linearity property, the left-hand side becomes the Laplace transform of y prime plus 3 times the Laplace transform of y is equal to the Laplace transform of the unit step function u of t minus 2. So from the table, the Laplace transform of the first derivative y prime is s capital Y of s minus y of 0. The Laplace transform of y is capital Y of s. This means that 3 times the Laplace transform of y is 3 capital Y of s. And this is equal to the Laplace transform of the unit step function, which is equal to e to the minus 2s over s, because alpha is equal to 2. And at this point we can substitute in the initial condition, y of 0 is equal to 1. So we can replace that y of 0 with 1. And this gives us s capital Y of s minus 1 plus 3 capital Y of s is equal to e to the minus 2s over s. So what we need to do now is to solve this for capital Y of s. So collecting the like terms on the left hand side for the y of s, this is equal to s plus 3 times capital Y of s. So bringing that minus 1 over to the right hand side, it becomes plus 1. So this is equal to e to the minus 2s over s plus 1. And then dividing by that coefficient, the s plus 3, we get the solution in the s domain that capital Y of s is equal to e to the minus 2s over s times s plus 3 plus 1 over s plus 3. So what we'd like to do now is use the table to do inverse Laplace transform and put this back in terms of the y in the time domain. So to do this, we need to get the answer in the same form as we have in the table. So we need to simplify the denominators. So start by looking at that term 1 over s times s plus 3. I'm going to use partial fraction decomposition to split this into a over s plus b over s plus 3. So you can use any method that you know to solve this to find a and b. So here I'm going to multiply through by the left hand side denominator, the s times s plus 3. And this gives me that 1 is equal to a times s plus 3 because the s cancels, plus b times s because here the s plus 3 cancels. So this equation is true for all values of s, so I can pick any two values that I want, and this would give me simultaneous equations to solve to find a and b. However, here I can choose particular values that will eliminate a or b. So if I want to find a, I can make the b vanish by choosing s equals 0 because b is multiplied by s. So here, substituting s equals 0, this gives me 1 equals a times 3 plus the b times 0. So solving this, I get a is equal to 1/3. So similarly, I can make the a vanish by choosing s plus 3 is equal to 0 or s is equal to minus 3. So substituting s equals minus 3, I get that 1 is equal to a times 0 plus b times minus 3. So dividing by the minus 3, I get that b is equal to minus 1/3. So therefore, the 1 over s times s plus 3 is equal to 1/3 over s plus minus 1/3 over s plus 3. So using the answer from the partial fraction decomposition, I can rewrite the solution capital Y of s as being equal to e to the minus 2s multiplied by 1/3 over s plus minus 1/3 over s plus 3 plus 1 over s plus 3. So now what I want to do is to rewrite this in the exact same form as I have it in the table. So expanding the brackets, I can say that capital Y of S is equal to e to the minus 2s times a third over s plus e to the minus 2s times minus a third over s plus 3 plus 1 over s plus 3. That first term, the e to the minus 2s times 1 over 3s, I want to rewrite this taking the third out to the front. So this becomes 1/3 e to the minus 2s times 1 over s. So that second term, I want to get a 1 over the s plus 3, so it's comparable with the table. So bringing the minus third out to the front, this becomes minus a third e to the minus 2s times 1 over s plus 3. And again, the 1 over s plus 3 would be 1 times 1 over s plus 3. So now what I have in the brackets is directly comparable with what we have in the table. So to do the inverse Laplace transform, we're using from the table that the Laplace transform of u of t minus alpha times y of t minus alpha is equal to e to the minus alpha s capital Y of s. So for these terms with the e to the minus 2t, this means we're going to get the unit step function of t minus 2, because the alpha is equal to 2, multiplied by inverse Laplace transform of that fraction that it's multiplied by, but then we have to substitute what we normally get for the t with the t minus 2. So for that first bracket, the e to the minus 2s times 1 over s. So the e to the minus 2s gives us u of t minus 2. And then we multiply by the inverse Laplace transform of 1 over s, which is 1. For the second term, we have minus a third. So again, the e to the minus 2s means we've got the unit step function of t minus 2. And then we do the inverse Laplace transform of 1 over s plus 3, which is e to the minus 3t. But because it's multiplied by that e to the minus 2s before the inverse Laplace transform, we have to replace the t with t minus 2. So it becomes minus a third e to the minus 3 times bracket t minus 2. And this is multiplied by u of t minus 2. And then for the last one, we have the inverse Laplace transform of 1 over s plus 3, which is e to the minus 3t. And this gives us the final answer.